Our work explores how robots can learn efficiently when the state of their environment is unknown. This is extremely common in robot problems where something like sensor noise or an object occlusion would prevent the agent from reliably measuring its state. In these instances, we can model the problem as a POMDP, but performing optimally would generally require the agent to remember all of its lifetime observations. Fortunately, this can be avoided by tracking a belief, which is a distribution over the states that captures the environment's uncertainty. The belief is a sufficient statistic for the history of observations, meaning we can substitute it without loss of optimality. This makes the belief very powerful when solving POMDPs. Unfortunately, tracking the belief is usually possible only in simulation. So we investigated how we could use the belief to virtually train a robot and then transfer the learned policy to physical hardware. This meant that we required a solution that could be informed by beliefs, but would select actions based on observations. Recent works have addressed POMDPs by training deep recurrent reinforcement learning agents to learn a mapping from the observation history to a policy. This is a good idea, but learning end-to-end like this is hard because the reward signal doesn't provide much instruction when it comes to which observations are important to remember. So others have tried circumventing this by feeding state information directly to the agent during training in simulation. But for this to work, there must be a rough correspondence between states and observations. So this might work well, for example, in visuomotor control tasks where there are no object occlusions, but it would not work well for arbitrary POMDPs. So in contrast, we introduced a belief-grounded network, or BGN, where we use the belief to guide the agent towards a good policy by teaching it to predict the belief from partial observations. To see how this works in practice, we can consider the A2C algorithm. This reinforcement learning agent has two recurrent networks, a value function for estimating its expected returns, and a stochastic policy network. The algorithm learns by repeatedly sampling short trajectories of experience, fitting the value function to the earned returns, and updating the policy by increasing the probabilities of good actions. Our BGN extends these networks with additional branches, shown in blue, that learn to predict the belief from the neural network's extracted features using softmax layers. During training, we minimize the cross entropy between the true and predicted beliefs jointly with the standard A2C loss, causing gradients to backpropagate into the main networks and encourage them to learn Markovian features. After training, these extra branches can be removed, and we get an A2C agent that requires only observations as input, meaning we can easily transfer it to a real robot. And this methodology is identical for other algorithms, so it's easy to substitute something like DRQN or PPO as well.
We have several baseline ASCS is an active critic agent taking history of action and observations. True beliefs are used for the critic in the ASCB agent. The critic in ASCS uses states, another form of privileged information. ABCB has true beliefs for both the actor and the critic. SASOF is an applied POMDP solver. We apply belief-grounded networks to ASCS, which we could call ASCS plus BGN. We first experiment with classical POMDP domains with aliasing states and noisy observations. In these domains, our method works as well as ABCB does. It also has comparable performances with SASOP and outperforms the remaining baselines. We also experiment with three robot domains under partial observabilities. For instance, in top plate, the agent has to grab the plate on top of a pie with a random height. Since the plate's position is unobservable, the agent has to use the soft finger to scan plates and relies on the finger's angle and position to localize the plate first.
Our method achieves 100% success rates in all tasks, beating every other method here. Especially, it's doing better than ABCB, which also use ground truth beliefs, because our method can learn good feature representation of the input histories even when the reward is sparse. The video here shows the performance of a UR5 robot when executing the policies learned by our method for top plate and 2-2D. We can see that the robot can achieve the goal effectively by grasping the top plate at an unknown position in a pile and grasping the bigger bump at an unknown position on a 2D plane. This image visualizes the belief during execution in 2-1D. We can see that BGN can reproduce the shape of belief accurately. Conclusion: in this paper, we introduce the belief-grounded network, which can accelerate the learning and partial observability using belief reconstruction loss. It requires no belief access during execution, and therefore it can be easily deployed in the real world. It outperforms baselines on different domains, and the policies it learns can work on real robots without fan turning. Thank you.